Okay, let's look at the integral test for series. So what's happening is it's not always easy to find the exact sum of the series. And so we're about to start looking at a bunch of different tests which will help us determine whether a series is convergent or divergent without finding the exact sum of the series. So when you can find a formula for the sum S sub n and evaluate that exactly, that's terrific. But lots of times that's just really hard to do. So we settle for, hey, can we at least find if it's convergent or divergent? So that's what we're looking at. The first test is the integral test. And it says suppose that a function is continuous, positive, and decreasing. So those are our three conditions. It's got to be continuous, positive, and decreasing from 1 to infinity. And then the series version would be just where you look at the domain of integers, positive integers, n. If that's true for the function x from 1 to infinity, then the series a sub n is convergent. If and only if we take the integral from 1 to infinity of f of x dx, if it is convergent. So what this basically means is if this series meets the condition that we looked at it, the function version of it, f of x, and it's continuous, positive, and decreasing, then we can apply this test. These are the conditions to apply before we apply it. Okay, so let's say it does. Then if we evaluate the function version, f of x, from 1 to infinity, and we find that this integral converges to some number, then we say that it's convergent. If the integral diverges to some number, then we say the series is divergent. So let's proceed. The first example we have is the series 1 over n squared plus 1 from 1 to infinity. And it says determine whether this series converges or diverges. So let's have a look at this. Is this continuous? So if we had the function f of x, the version would be 1 over x squared plus 1, okay? The domain is all real numbers, and so it's continuous on its domain for a rational function, and so it's certainly continuous from 1 to infinity. It is positive because we have a positive 1 over x squared is a positive number, plus 1 is also positive. It's always positive. And is it decreasing? So let's check the third condition for decreasing. I'm going to do this using calculus. Let's take the derivative f prime of x, which is equal to, this is quotient rule, low d high, so it's going to be low, x squared plus 1, derivative of the numerator d high, minus high, 1, derivative of the denominator 2x, all over the denominator squared. Okay, and so 0 times anything is 0, minus 2x all over x squared plus 1 squared. Well, if we're looking at terms from 1 to infinity, and we are, if you put any x values in 1 to infinity, negative 2 times that is going to yield a negative number in the numerator. And something squared is going to be positive. So we're looking always at a negative divided by a positive, which means that f prime of x is always negative on this interval. And so what that means is that the function itself, the function f of x itself is always decreasing on this interval. So if it's always decreasing, then it meets that condition. So that means, okay, yay, we can apply the integral test. So let's look at the integral from 1 to infinity of f of x dx. So let's go ahead and write this is how we deal with improper integrals, and this is improper, from 1 to t of 1 over x squared plus 1 dx. All right, so if we're going to integrate this, this x squared plus 1 is a known integral. This is tangent inverse. So this is the limit as t goes to infinity of the antiderivative, which is the tangent inverse of x, 1 to t. All right, so this is the limit as t goes to infinity of the tangent inverse of t minus the tangent inverse of 1. All right. Well, if you remember the unit circle, or if you what angle yields a tangent that's undefined, you might remember that this is pi over 2. Or if you think of the graph of the tangent inverse, kind of does this, and as t goes to infinity, it's approaching this value right here, and this value is pi over 2. So the tangent inverse of infinity is going to be pi over 2, and the tangent inverse of 1 is going to be right here on the unit circle, pi over 4. All right? Pi over 2 minus pi over 4 is pi over 4. Okay, so what just happened? Well, what just happened is we said, hey, does this series, its function equivalent, meet the conditions? Is it continuous? Is it positive? Is it decreasing? And yes, yes, yes. So we applied this test. We took the integral from 0 to infinity of this, and we found that it did converge to a number. The integral converged to a number. What does that tell us? That tells us, we say, the conclusion, which I'll write in the middle of all this, from all of this work we just did, is that this series n is 1 to infinity of 1 over n squared plus 1 converges by the integral test. That's what we just, I'll kind of highlight that a little bit. That's what we just decided here, and that's true. So there's a couple of things we want to take note of over here, right? One is that when we apply the integral test, if it converges, okay, whatever the integral converges to is not what the sum of the series is. We have not just calculated the sum of the series. So the value, okay, I'll just say the sum, let me write it like this. We are not calculating the sum of the series when we evaluate the integral. And so what I'm trying to say here is that whatever the integral converges to, in this case pi over 4, that isn't, we did not just calculate the sum of the series. We just determined that the integral converged to some number, so we can say that the series does converge, but we don't know what the sum is of this whole series. So just be careful. This does not mean that this is the sum of the series. That's what I'm trying to say. The second thing that I would like to take note of is that if n doesn't start at 1, but it starts at 2 or 4 or 7 or some number later down the road, that's okay. We can still apply this test. So if it's overall decreasing, so n does not have to start at 1. Okay, that is another good thing. And then the other thing I wanted to point out is that if the function is decreasing, but like maybe the first few terms are not what am I trying to say? The first, like maybe it starts off, it goes like 1, and then it goes 2, and then it goes back to 1/2, and then it goes 1/3 and 1/4, and then it starts decreasing after that. As long as it's overall decreasing, as long as the series is overall decreasing, like as n goes to infinity, it's decreasing. Like at the beginning, it's not decreasing. You can still use this test. Still use this test. All right, so that's what I wanted to kind of point out. Let's look at number 2. It says determine whether the series converges, diverges, and so we notice here that this one doesn't start at 1, but we know that that's okay. Okay, so let's test this out. This equivalent is f of x is 1 over 2x plus 7 cubed. Okay, this is the equivalent f of x. So let's see here. On its domain, is it continuous? Yes. And it's the only problem that the domain would be where 2x plus 7 was 0, or x is equal to negative 7/2. Okay, but that's not on 1 to infinity. So on its domain, it's continuous. On its domain, it will be positive because we're putting in, or from 1 to infinity, it will be positive. So it's continuous, it's positive. Is it decreasing? Well, let's take a derivative here. And so this is L'Hopital's rule. Low, 2x plus 7 cubed, derivative of 1 is 0, d high, minus high, 1. Derivative of low is 3 times 2x plus 7 squared. Chain rule times another 2 over low, 2x plus 7 to the 6. Okay, let's see what happens here. Excuse me. Let me see. This is going to be 0, and this is going to be a negative 6 times 2x plus 7 squared over 2x plus 7 to the 6. Okay, we have something squared, which is positive, times a negative, which gives us a negative, over a positive, which means it's negative. What does that mean? Well, the derivative of x is negative for all x on 1 to infinity, so that means the function f of x itself is decreasing like we needed it to be. So we'll say f of x is decreasing. So it met all the conditions. That's what we were checking off. So let's apply. Now we say, okay, let's apply the integral test. And so I'm going to go ahead and rewrite my improper integral into a limit. The limit as t goes to infinity from 2 to t of 1 over 2x plus 7 cubed dx. So let's integrate this guy. This is going to be u substitution. I'm going to let u equal to 2x plus 7 du will be 2 dx. So 1/2 du is dx. If I rewrite my integral into u, I'll have 1/2. By writing down 1/2 du, I've got the dx. So this is going to be u to the negative 3. Let's integrate, and then I'll put my limits back in. This is u to the negative 2 divided by negative 2. So that's going to be negative 1/4 times 2x plus 7 to the negative 2, or 1 over this squared, right? So let's evaluate this from 2 to t, the limit as t goes to infinity. All right, let's see. What do we get there? This will be 1/4 times 1 over 2t plus 7 cubed minus, let's see, this should be negative 1/4 times this, and then minus 1 over 2 times 2 is 4, plus 7 is 11 squared. That's what I get here. All right. And this is the limit as t goes to infinity of all of this stuff right here. All right, so as t is going to infinity, 2 times infinity plus 7 cubed is enormous, and this is going to 0. All right, so what this is equal to is just going to be negative 1/4 times negative 1 over 11 squared, which is 121. A negative times a negative is a positive. I get 1 over 484. So what did we just discover? Okay, that's what the integral equals to. Fine. The integral converges to a number. Fine. This is not the sum. We just needed to know that it converged. So our conclusion here is that this sum converges. by the integral, test. That's what we could conclude right there. Okay, just a couple of more examples.